Hi, this is Keshav of CSE Data Science. Today our topic today our topic was application of quantum mechanics in magnetic resource imaging (MRI). An introduction. Nowadays there are many techniques to observe and analyze the inside of the human body in order to obtain a better diagnosis. One of the invasive and high resolution technique is the magnetic resource imaging, which takes advantage of hydrogen nuclei, a powerful static magnetic field, and a computer system to process to get the images. The nuclear magnetic response is a physical phenomenon in which certain atomic nuclei with odd number of protons and neutrons are placed under the high intensity magnetic field can selectively absorb energy from electromagnetic waves in the radio frequency range. Once the nuclei have absorbed in energy, the excess energy returns to the surroundings through a process called relaxation, which is accompanied by the magnetic variation, which includes a signal receiving antenna for a processing and thus obtain an image or perform a spectrometric analysis. MRI equipment consists of magnetic, usually superconductor radio frequency coils, magnetic field radiance, a bore or tunnel, a computer signal processing. MRI requires the use of high intensity magnetic field. Clinical equipment use field strengths ranging from 0.5 to 3 ton, which have been achieved by the placing the permanent magnets by superconducting electromagnets, resulting in a very wide line research. BCS theory is a dominant physical theory of superconductivity and was proposed by the John Bardeen, Leon Cooper, and Robert Schrieffer. The theory is based on the fact that charge carriers are not free electrons but rather pairs of electrons known as Cooper pairs. Although the electrons are Fermionious and the subject to Pauli exclusion principle, being a crystal lattice, the energy between them becomes negative, so that the pairs are created to minimize the energy and behave as bosons. In this proper, we discuss the basic physics involving magnetic resonance, providing an analysis from the viewpoint of quantum mechanics. The hydrogen atom. MRI uses the properties of hydrogen nuclei when they are exposed to a high magnetic field and the radio frequency field, so that it is important to analyze the physical characteristics of hydrogen atom. The hydrogen atom is the simplest atom since there is a proton in its core and the electron obtaining the experimenting and attractive Coulomb potential. V of r is equal to E square by 4 pi epsilon naught r. Let us consider this as equation 1. To perform the analysis of the Schrodinger equation independent of the time used, h psi r is equal to p square by 2 nu plus v of r into psi r is equal to E psi r. Let us consider this equation as equation 2, where nu is reduced mass of the system and p momentum operator. Nu is equal to mp into mg by mp plus me. P is equal to minus IH delta, where mu is reduced mass of the system and P is momentum operator, where because there is a central potential, V natural coordinates are the spherical coordinates, and equation 2 becomes minus h cut square by 2 mu r square sin theta by sin theta dou by dou r of r square into dou by dou r. By realizing above equation, we get psi into r comma theta comma phi is equal to r of r y of theta comma phi. Nuclear magnetic resonance. Nuclear magnetic resonance is a physical phenomenon associated with the intrinsic angular momentum of the spin and the magnetic properties of atomic nuclei. When the nucleus is placed in the magnetic field, an interaction occurs between the magnetic moment of the nucleus field, resulting in an energy splitting by the absorption of and emission of the photons with the right frequency transaction between the energy states may occur. Local magnetic changes produced by the absorption and the emission of the detected by the antenna that sends the signal to the computer of decoding image generating. Nuclear magnetic resonance is a physical phenomenon associated with the intrinsic angular momentum of the spin and the magnetic properties of the atomic nuclei. When the nucleus is placed in the atomic field, an interaction occurs between the magnetic moment of the nucleus and the field, resulting in energy by splitting the absorption and emission of the photons with the right frequency. Transition between these energy states may occur. Local magnetic changes produced by the absorption and emission of the detector by an antenna that sends the signal to a computer for decoding the image generating. Nuclear spin. The particles that make up the atomic nuclei have the intrinsic quantum mechanical property of spin. In the nuclear physics, the total angular momentum that the nucleus has called the nuclear spin. Through the term should not be confused with the spin of each nucleon or the total spin as the sum of all nucleons, because this is just one or two of the contributions to the nuclear spin. The other is angular momentum of the nucleon, so that each nucleon will have a net regular momentum such as that. Then the nuclear spin will be J is equal to sigma I J I is equal to sigma I L I plus S I, or just J equal to L plus S. Each of these vectors have a similar quantum number magnitude of the orbital angular momentum satisfies L square is equal to L plus 1 h cut square con L is equal to 0, 1, 2 and so on. The direction of angular momentum vector L is associated with the atomic number m for the given quantum orbital momentum number L. There are 2L plus 1 integral magnetic quantum numbers arranging from the z-axis component of angular momentum is given as Lz is equal to mi h cut. For the vector of the spin angular momentum S, its quantum number can take the integer or half integer values. S square is equal to S into S plus 1 h cut square con S is equal to 1 by 2, 1 by 3, 3 by 2. For the z component, we find the Sz square ms of h cut, whereas there are two s plus 1 values of the ms to exhibit the property of MRI. Nucleus must have a non-zero value of S in the medical applications. The proton is the nucleus of the most interest due to its high natural abundance. However, other nuclei have been studied. The proton is a pheromone for those value of S is 1 by 2. Therefore, there will be no two possible values of for SZIA plus or minus h by 2. The eigenfunctions describing the nucleus can be written as L plus 1 by 2 and minus 1 by 2. Since quantum mechanics, every physical observable has an associated operator, then we can write the eigenvalue equation to describe the observation of the spin state as Sz by ms is equal to ms by ms, where Sz is equal to operator describing the measurement of angular momentum along the z-axis. Voxel magnetization. To measure the energy of the spin system, it is necessary to construct a Hamilton operator. The shape of the Hamilton can be derived from the classical electromagnetism for the energy of a magnetic moment placed in a magnetic field. The nuclei have the magnetic moment mu bar, which is proportional to the spin angular momentum, where gamma is a constant of the proportionality called gyromatic ratio, which is a proton. It's a value of 2.675 into 10 power 8 radian per second. In the magnetic placed in the magnetic field B, the ground state is degenerated with the particular level will be. Combining equation 6 and 7, the Hamilton is obtained, and since B is oriented in the z direction, the Hamiltonian becomes. Now using Schrodinger's equation, the energy eigen states are found. Zeeman splitting is shown in the figure 1, whereas it shows the intensity of the magnetic field increases energy spin up and spin down, where the latter has higher energy state than the spin up state. Between two states can be induced by the absorption or emission of the photon such that excitation of magnetization by radio frequency pulse. A volume A volume of the element of the sample defined as a voxel having a placed at the transmitting antenna in the direction of maximum emission to the voxel in the vertical plane, and the changing the transmission frequency when we emit the frequency of the precision. The nuclei are able to absorb energy, enter resonance. When the nuclei of the voxel are entering into the resonance, magnetization vector M travels performing a spiral rotational movement related to the direction of field B0. Such the nucleus is entering into the resonance at the specific frequency prescribed by the Larmor law, depending on the B0 perceived and the biochemical environment is located. Therefore, the radio frequency emission contains an approximate bandwidth of 100 kHz. Separation of the M with respect to the equilibrium position is determined by the angle of inclination or flip angle. Its value depends on the power of time of radio frequency emission among the other factors. A 90-degree pulse moves the magnetization vector about the x-y plane, and the 180-degree pulse inverts the magnetization respect to the equilibrium position. After a 90-degree pulse, the longitudinal component of the magnetization vector is 0. In this position, the number of nuclei in the lower energy states equals the nuclei in the higher energy state. It is called the state of saturation. Conclusion: MRI is a technique that is visualizing tissues that makes use of physical phenomenon nuclear magnetic resonance with the union of quantum mechanics with the classical electrodynamics that uses the quantum mechanical properties of the hydrogen atom to produce high resolution images that help with the medical diagnosis. Nowadays, there are many MRI machines used for both medicine and research, where the second case it is essential to have the knowledge of the facets at a quantum level of the physical process involved. Likewise, there is a wide variety of the research topics such as digital processing of the images acquired during a study, magnetic resonance spectroscopy, frequency coils, pulse frequency design, etc. The bread field development is a monitoring research. Thank you.